Okay, so let's get started. Today will be a review lecture, and it will be highly based on the summary that I posted online. So just underneath the textbook on the website, there is a summary .pdf. It's just a bunch of bullet points which I'm going to cover today as an overview of everything that we've done in the course. Let me start with announcements first, though. So assignment 6 is due Friday, and there will be no late assignments so that I can post a solution on Saturday. The exam is next Thursday, on the 7th of May at 3 p.m. Central Time, so 2 p.m. for School of Mines, and it's in the DDN rooms. So I've sent you an email with that information. The exam is 2 hours long, and you can bring 5 pages of handwritten notes. So 2.5 sheets of paper, double-sided. I think that's all about the exam. Yeah, that should be all very soon with the exam. And then a reminder to please fill in class evaluations or course evaluations. And so you need to go to your admin office and get a form and fill it in. Since there's no class on Thursday, maybe you can take the time on Thursday to do that instead. Or do it ahead of time. Thanks. Any questions? Okay. So if not, I'd like to do a summary of everything that we've learned in the course. This is all material that you could expect to be on the exam, and of course some of it will be on the exam. It goes without saying that some of the derivations are, I can't expect you to memorize. It wouldn't be very smart for me to expect you to memorize the derivation and things like that. So that's not the kind of test that this will be. But however, I do expect you to understand the points. So if you struggle understanding these bullet points, you need to go study and make sure you understand them. Okay? So the exam will test your comprehension as well as your ability to apply the material on physical systems. Well, I guess I could remind you in the announcement that there's no lecture on Thursday. Okay. So the first thing we did was that we motivated the use of generalized coordinates. And those generalized coordinates are typically a set that we've labeled qi, where I can go from 1 to n. And those coordinates, remember, are functions of time. And the idea is that you have exactly the right number of coordinates as you do degrees of freedom. So the number of degrees of freedom, n, is the minimum number of numbers that you need to fully describe the system. And the goal of classical mechanics, or any mechanics, is to find out what the functions qi of t are. So then you know, since the qi fully describe the system, and you know how all of the qi evolve with time, you can describe how the system evolves with time. So that's the goal. We saw that this was straightforward. In holonomic systems. Straightforward. And holonomic systems. So what's a holonomic system? A holonomic system is a system where you have holonomic constraints. Remember, holonomic constraints are constraint equations between the coordinates. So if you have equations that relate the coordinates to each other, necessarily those coordinates are not independent. And so you can always use a holonomic constraint to eliminate coordinates. And then it becomes pretty obvious how many degrees of freedom you have. So an example of a holonomic constraint is, if you have a block sliding down an inclined plane, this is a two-dimensional system, right? Because the block will move in both x and y directions. However, the block is constrained to be along the ramp. And so you have a constraint, if this is some angle theta. The constraint is that the y position of the block over the x position of the block is given by a constant. And so y is equal to x tan theta. And you can always express y in terms of x. That's a holonomic constraint. So you can always get rid of y's. Sometimes non-holonomic constraints can be made holonomic. An example is rolling without slipping. So in principle, rolling without slipping in 2 dimensions or in 3 dimensions is not holonomic. But we saw in a lot of cases when it's 1-dimensional rolling without slipping, that you can integrate the non-holonomic constraint into a holonomic constraint. So rolling without slipping in 1D is actually holonomic. The constraint for rolling without slipping, remember, is that the point of contact of the rolling object is instantaneously at rest. So that's a condition on the velocity of the point of contact. But if it's in 1 dimension, you can integrate that out with respect to time and get a relationship between, say, the angle of rotation of the thing that's turning and the distance that it's rolled along the surface. We showed that we can describe a system by specifying its path through an n-dimensional configuration space. So for a cannonball, for example, the goal would be to describe, so in 2 dimensions, let's say x and y, so that would be our configuration space. The goal would be to describe the path of the cannonball through configuration space. And that path, multiple paths are possible with the laws of physics that we have, the laws of physics in this case being gravity. And the specific path that is taken in configuration space depends on the initial position in configuration space as well as the initial velocity in configuration space. So the path depends on initial position in configuration space and initial velocity in configuration space. And as you know, that's not the case in phase space. In phase space, it's determined uniquely by the starting position. Whereas in configuration space, you also need to specify the velocity. Then we took a break, a mathematical interlude, and we introduced the techniques of the calculus of variations. One particular problem that we were interested in was that of finding the stationary value of some integral of some function of the coordinates. So we found that we can find the stationary value of this integral, and the idea is to find the QI's of t that make this integral stationary, and those functions QI of t were given by the Euler-Lagrange equation. So the Euler-Lagrange equations tell us, or give us, let's say they give us instead of tell us. The Euler-Lagrange equations give us differential equations to solve for the QI of t. So I hope you know this by heart. The Euler-Lagrange equation is d by dt, so total derivative with respect to the independent variable of di L by di QI dot minus di L by di QI equals to 0. In order to derive this, at one point we had to impose that the QI's are independent of each other, because we had to do a variation of the integral, and we needed to be able to say that the QI's can be varied independently. But in some cases, you might want to have more QI's than you need, more than the number of degrees of freedom. So maybe you have holonomic constraints and you've included additional QI that you don't really need. And we found that there's a clever way to deal with that, we found that we can use Lagrange multipliers to deal with situations where the QI are not all independent, to deal with cases where not all the QI are independent. For example, if they are related by holonomic constraints. And that was the main thing that we really needed to borrow from this mathematical interlude. Then we went back to physics. And we introduced the concepts of generalized force, to accompany our generalized coordinates. And these generalized forces were a start in moving away from a vector-based description of classical mechanics. And the Newton's second law is vector-based, and more scalar-based description. So as a start, we introduced the concept of generalized forces, and then modified or rearranged Newton's second law to get D'Alembert's principle. Right down on the next page. D'Alembert's principle related the total kinetic energy of a system, so it is d by dt of di capital T by di qi dot minus di capital T by di qi. That was equal to capital QI, or capital QI in this case, was a generalized force. So if you remember, if you want to calculate a generalized force, you still have to make a diagram and draw out vectors. And you have to figure out what the position vector was for each force, and you have to do a little bit of variation, and then ultimately you can end up with a scalar. But it was hard to write out a generalized force without drawing out a vector. So it's kind of halfway there. So D'Alembert's equation is very much like F equals ma. So F is the Q, and then the ma is the things with the kinetic energy. So we've gotten rid of the acceleration vector, and we've replaced it with the kinetic energy, which is a scalar. So we're getting there. At this point, we made an argument that in nature, a lot of the forces that we see are conservative or monogenic. That's basically the same thing, except monogenic is just a little bit more general term than conservative, and monogenic just means that we can include electromagnetism, because electromagnetism depends on the velocity of the particle. So the magnetic force, Q V cross B, depends on the velocity of the particle. So we have to extend it not just the conservative forces, but a little bit more so that electromagnetism would work. For most of the forces in nature, if you consider a system from a global enough perspective, ultimately you only have the four fundamental forces at play. Right? You have gravity, the weak and strong interaction, and electromagnetism. And all of those are conservative or monogenic. And in most physical systems of this size, it's only gravity and electromagnetism. So that was a fairly strong argument. So we restricted ourselves to conservative or monogenic forces. The reason we cared about using conservative and monogenic forces is because you can use a potential energy and then take the gradient of that potential energy to get a force. So any force that you have that's conservative or monogenic, you can express as some function of a potential energy, which of course is a scalar. So this allowed us to introduce, so we then introduced the Lagrangian L, and so L was given by the kinetic energy minus the potential energy. And that means that the generalized force with capital QI that you have in D'Alembert's equation can be written as a function of the capital D. And so we could rewrite D'Alembert's principle as d by dt of di L by di Qi dot minus di L by di Qi equals to 0. So what we've done here is we figured out how the generalized force Qi depends on d, so that we could then move it to the left-hand side and only have scalars involved. So this leads to n, where n is the number of degrees of freedom, second order ordinary differential equations for the functions Qi and t. That really was the ultimate goal. So now we have at our disposal a framework that's based only on scalars and allows us to describe pretty much any physical system and how it evolves with time. Now we compared this equation to what we found in our mathematical interlude, and we saw that it's exactly the same equation. All right, when we derived this equation here from D'Alembert's principle, we didn't do any variational calculus, at least not the Euler-Lagrange part of it. All we did was start from Newton's second law figure out a clever way to write the acceleration in terms of the kinetic energy, and then we arrived at this equation. And then we got rid of the forces by making them derivatives of potentials, and then we got the definition of Lagrangian and the equations of motion. And then we observed that that's exactly the same equation that you get from the Euler-Lagrange equation. So we observed that this is the same as the Euler-Lagrange equation from variational calculus. So we recognize Hamilton's principle and used it as our basis for classical mechanics. I'll put it with a capital L this time. So we observed that D'Alembert's principle gives us something that looks like the Euler-Lagrange equation. And so Hamilton's principle is that the equations of motion, call that HP, the equations of motion are given by requiring that the action be stationary. So the action S is given by some integral from t1 to t2 of some function L that depends on the things you want to know, qi, qi dot, and dt. So the fundamental principle now is that we need to find the functions qi such that this integral is stationary. And we know that if we define L to be t minus v, then for sure we get Newton's second law. So we know that if we define L to be t minus v, then this is equivalent to Newton's second law. So then we flip it around. And we say this is the fundamental principle. It's not Newton's second law anymore, which is what we used to build up to here. We know we get the right answer, so now we make this the fundamental principle, and then we know that Newton's second law will agree with this. And that's fine, right, from a physics perspective. There's nothing fundamental in Newton's second law. Scientifically, Newton's second law is correct because we do experiments, and all the experiments that we do agree with Newton's second law. So there's nothing more fundamental to it. Right? Newton could have written some other law and it could have been wrong. It's only correct because experiment seems to agree with Newton's second law. So since all the experiments agree with Newton's second law, then all the experiments will agree with this as well. So let's make this the fundamental thing. That's sort of the idea. So maybe if we make this the fundamental thing, then we get more insight into classical mechanics. And indeed, that was the case. If you use Newton's second law, it's not immediately apparent that energy and momentum should be conserved. it turns out that it is. I mean, the second law does lead to conservation of energy and momentum, but it's not as obvious or as pretty. You don't get as much insight as when you use this, the action, or Hamilton's principle, as the fundamental thing. But it also turns out that this action is the fundamental principle behind quantum field theory. And so in quantum field theory, and even quantum mechanics, we say that the laws of motion are governed by the principle of least action. That's exactly what this is. The principle of least action means make the action a minimum. And we don't need to care if it's a minimum or a maximum, so we just say stationary. Okay, but this is the principle of least action. Okay. So, if we really needed to, we saw that we can use Lagrange multipliers to find forces of constraint. It's not quite true that we don't want to use forces. I mean, forces can be interesting, right? Forces can be useful. You can find out when stuff breaks based on forces. So we did an example of a block sliding down a hemisphere, and when does it fall off the hemisphere? And that turned out to depend on the normal force. So just because forces are ugly and annoying doesn't mean that they're always completely useless. They're usually ugly and annoying, but they're sometimes quite useful. So we can always find out what they are by going back and introducing holonomic constraints, typically, to find the forces associated with them. Let's say, well, if needed at the end of that sentence. Then we started to look at this Lagrangian way of doing physics, and we saw that it encompasses a lot of neat things. We saw that conservation of energy was built in. To the formalism. In particular, if the Lagrangian didn't depend explicitly on time, you take the partial derivative with respect to t and you got 0, and we found that this thing, lowercase h, which we call the Jacobi integral, and that's defined to be the sum from I equals 1 to n over the number of degrees of freedom qi dot times di L by di qi dot minus L, sorry, let's close the parenthesis and then minus L, then we found that dH by dt was equal to 0, or h is equal to a constant. And in particular, if t is quadratic in the velocities, quadratic means that t was the sum over I and j of aij qi dot qj dot, and v does not depend on the velocity, then this quantity h, the Jacobi integral, was equal to T plus D, the total energy of the system. So those two ifs are often true. So T is often quadratic in the velocity, and V often doesn't depend on the velocity. So this quantity h that's conserved when dIL by dt is equal to 0 is often the total energy. So it's actually more general than conservation of energy, because h can still be conserved even if it's not the total energy. When we saw that momentum, we saw that conservation of momentum is also built in to the formalism. In particular, we introduced the generalized momentum Pi that goes with generalized coordinate Qi. We define that to be dIL by dQi dot. So if I go back and I look at the Euler-Lagrange equation, right, for the equation of motion, I have d by dt of dIL by dQi dot. The dIL by dQi dot is Pi, right? So if I write the Euler-Lagrange equation with Pi instead, I have d by dt of, we just said that thing is Pi, minus dIL by dQi equals to 0. So if dIL by dQi itself is equal to 0, we say that Qi is cyclic, if that's the case. What that means basically is that the variable Qi doesn't appear inside of L. So then of course when you take the partial derivative of L with respect to Qi, you get 0. So that's a cyclic coordinate. So dIL by dQi is equal to 0, and you get that dPi by dt is equal to 0. And when d by dt of something is equal to 0, then something is constant. But this Pi is generalized momentum. It does not necessarily have the units of linear momentum. And in fact, we saw that for rotational systems, when maybe Qi is an angle instead of, an xy or Cartesian v, in that case, the Pi often turned out to be an angular momentum instead of a linear momentum. We actually saw that this conservation of momentum that's built in was true for linear and angular momentum. So in this new framework, we don't have all this patchwork of tools that we need to combine and choose what's the best option to solve a problem. Right? In vectorial mechanics, you might have a problem where here you better use Newton's second law, whereas for a different problem you're best off using conservation of energy, and for another problem you're best off using torques. So we didn't need to do that. It's just natural. There's just one way of doing it, and whatever conserved quantities will just come out. Then we decide, okay, well, how do I find out what the conserved quantities are? So the next thing we did was we used Noether's theorem to generalize the idea of conserved quantities. Let's make that plural. So we used Noether's theorem to generalize the idea of conserved quantities. And in particular, we found that this is the theorem, for any continuous transformation, so we defined what continuous transformation meant. So for any continuous transformation that leaves the action unchanged, there exists a conserved quantity Q we label it capital Q. So this is the second of three capital Q's that we use here. So there exists a conserved quantity capital Q, and that quantity capital Q is given by, there's a sum over the degrees of freedom, n equals 1 to n. The generalized momenta Pi, times Fi, I'll come to Fi in a second, plus the second thing, G, times the sum of I equals 1 to n of Pi Qi dot minus L, where the sum is only over the thing with the i's in it, not the L. And so just, you might think the notation is not very smart because I had capital Q earlier for generalized forces. Maybe that's a mistake. Now I have capital Q for a conserved quantity, and then you know that I'm going to have capital Q when I do canonical transformation. So this capital Q here, it actually comes from Noether's original theorem, and the conserved quantity was called a charge. And so we use Q for charge. Noether's theorem is very general, and in fact it tells us things like why electric charge is conserved. So if you have to do field theory, so you have to do a continuous Lagrange, so Lagrangian density. If you do the Lagrangian density for electromagnetism, you find that you can apply some certain transformations that leave the action unchanged. And one of those transformations leads to a conserved quantity that's electric charge. And in fact, all things that are conserved come from Noether's theorem. And the more general version of Noether's theorem is actually applied in field theory, not in the discrete case that we have here. Okay, so back to the discrete case. Now what are these Fi's and Fg's? These Fi's and G's are something that has to do with the continuous transformation. So the continuous transformation is a transformation to a new set of coordinates Qi prime from the original set of coordinates Qi plus a small amount delta Qi. And we can write that small amount of delta Qi as some function Fi that's different for each Qi, so that function Fi will depend on all of the Qi's and the Qi dots and potentially T. So it's some function and then times a small number. So a continuous transformation was actually a transformation that you can make infinitely small, so almost like no transformation at all. And you can model a very small transformation as taking the original coordinate and then adding a function plus a very small number. And the small number, of course, is the tune how big you make the change. So that's what the SIs were. And then in principle, your continuous transformation could also transform time. So writing that just the same way, or some t plus some delta t, you can think of the transformation changing the units of time, or changing where t equals 0 is. And it's not that weird. So we write that as some separate function g that could also depend on the coordinates and the velocities in time, and time that small number. So what you see is that this conserved quantity, capital Q, has two terms in it. The first term is related to the transformation of the coordinates, and the second term is related to the transformation in time. The transformation, the time part, if you look at what's in parentheses there, that's exactly the Jacobi integral. So if the transformation is only, say, a translation in time, where g is equal to 1, then the conserved quantity is the Jacobi integral, which we'd already found. But this generalizes the concept. Well, the other way around, if there's no transformation in time, the g equals 0, and the transformations are either translations or rotations of the coordinates, then the conserved quantity q were typically linear momenta or angular momenta. Okay, so we recovered the two things I said earlier about whether L depends on t, then the Jacobi integral is conserved, or if some coordinates are cyclic, then the momenta are conserved. This includes both in a general way. And so then we saw some specific examples where symmetries in translation of the spatial coordinates led to conservation of linear momentum. Symmetries related to rotations led to conservation of angular momentum. And translations with respect to time led to conservation of energy. In general, it might not be easy to tell if a transformation leaves the action unchanged. So in a specific case, where the transformation does not involve time, that turns out to be a rather general case, right? Most of the coordinate transformations are of the coordinates and not so much of time. In a specific case where the transformation does not involve time, we showed that it is sufficient to test whether the Lagrangian is invariant. And that's much easier than to see if the integral is invariant. The integral being the action. Huh? Next, we introduce the Hamiltonian. Introduced H as the Legendre transform of the Lagrangian. So H which is a function of the QI, the PI, and the T, was given by the sum over the degrees of freedom PI times QI dot minus L. I'll write out here explicitly that L depends on QI, QI dot, and T. So it was very important in the Hamiltonian formalism to completely get rid of the QI dots. And we showed through the properties of the Legendre transform that H truly does not depend on the QI dots. Even though on the right-hand side, both L and the sum have QI dots, it turns out that that clever combination makes the total thing not depend on QI dots. That's a property of the Legendre transform. So the Hamiltonian depends independently on QI and PI. And it's easy to go back and forth between the Hamiltonian and the Lagrangian. So we promoted, another thing that we did, we promoted the PIs to the status of independent coordinates. So by that I mean that previously we described the system completely by specifying all of the QI and the initial speeds, QI dots, at some initial time. So instead of doing that, I now say that I can specify the system completely at any time by specifying all of the QIs and all of the PIs. And I have to specify two M things and describe how two M things is all through time. That's not so different, and in fact, of course, mathematically equivalent. So we promoted the PI to the status of independent coordinates, and the equations of motion are now given by what's called Hamilton's canonical equations. So since the system is now described by both QI and PI, we need to know what are the differential equations to solve that give me QI and PI as a function of time. And those differential equations in Hamilton's formalism are called Hamilton's canonical equations, and they are particularly simple. So QI dot is given by partial derivative of the Hamiltonian with respect to PI, and PI dot is given by minus the partial derivative of the Hamiltonian with respect to QI. And so this is 2n equations, and they are first order ODEs, ordinary differential equations. So it's mathematically equivalent to the Lagrangian formalism where you had n second order differential equations, because you can always write a second order differential equation as two coupled first order differential equations. So these are two coupled first order differential equations. And you can always convert these back into one second order differential equation. So you can combine these two equations into an equation for QI double dot. And we did a couple of examples of that in the tutorial on the Hamiltonian. And I encourage you to make sure you can understand how to go from these two first order differential equations to a single second order differential equation. Any questions so far? So then we saw that we can describe the motion of a system in a 2n-dimensional phase space. And the trajectories in this 2n-dimensional phase space, the shape of them, is uniquely determined by the Hamiltonian. And because this is a 2n-dimensional space, any position in that space specifies everything you need to know about the system, the positions and the velocities, in this case the momentum. And so, because the laws of classical mechanics should be deterministic, so if you have a system, you want to be able, and you know everything about it, you should be able to say how it's going to evolve. So if you think of having two paths in a phase space for two different systems that cross each other, that's not possible. Because if those two paths cross each other, that means there is a point in phase space where you don't know which path you should take. So the deterministic property of classical mechanics breaks down if paths are allowed to cross in phase space. Configuration space is fine, right? In configuration space, here you have two different cannonballs, and the two paths cross each other. With the same laws of physics determine the shape of the path, but the actual path itself is also determined by the value of the initial velocity. In phase space, that's no longer the case. For example, the example that we did in the notes was a simple harmonic oscillator with Hamiltonian equal to p squared over 2m plus a half k q squared. That's the Hamiltonian for a simple harmonic oscillator of mass n with a spring constant k. We saw that the path and phase space of that system, so if you draw, so you basically can only draw it for a 1 degree of freedom system, because the 1 degree of freedom system has, 2n coordinates in phase space, so 2. But if it's 2 degrees of freedom, then it would be 4, and you can't draw that. You can draw q, which you can think of the x position, and p, which you can think of as the momentum in the x direction. We saw that for a simple harmonic oscillator, the path and phase space is an ellipse. And then you could have a different system that would also follow an ellipse in phase space. And those two are never allowed to cross each other. And what distinguishes these two paths are different energies. So this could be path 2, and this could be path 1. And what determines which ellipse you're on is the energy of the system. So in this particular case, energy is conserved. Right, and so the Hamiltonian is equal to the total energy. And so you can look at this Hamiltonian to figure out what the points are where the ellipse meets the x and y axis. All right, so it meets the q axis, where let's say when this is equal to E2, when p is 0. And so here you'd have a half k q squared equals to E2. Whereas here, you would have p squared over 2m equals to E2. So you can learn a lot about the system by just looking at the Hamiltonian. Oh, I'm sorry. No, I think my connection has been okay. So there's people that didn't. Is there anybody that saw me continuously? Because I have two computers logged in, and I didn't see any issues with them. Seems to catch up. Interesting. That's hard because there's sometimes several seconds of lag between when I talk. That's why I always wait a long time for you to answer questions or to ask a question. So maybe I'll just reiterate that I was talking about phase space, and you can look at the shape of the Hamiltonian to determine the shape of the path taken through phase space. And for the example of a simple harmonic oscillator, that path is an ellipse because the whole total Hamiltonian is a constant equal to the total energy. And then in phase space, different systems will take different ellipses, and the different ellipses are related to the total energy of the system. So then we noted that this looks very much like the lines of a fluid in fluid dynamics. And then it turns out that you can describe motion in phase space using the equations of fluid dynamics. And that was kind of weird, but kind of interesting. Okay, so hopefully it's caught up. The next thing we did was we introduced Poisson brackets between functions of the canonical variables. So we say that Qi and Pi are the canonical variables. So they're the variables that we care about in Hamilton's canonical equation. Okay. So the Poisson bracket, so we have two functions of the canonical variables. So U, which depends on all the Qi's, all the Pi's, essentially time, and V, which depends on the Qi's, the Pi's, essentially time. The Poisson bracket, we use curly brackets. The Poisson bracket between U and V is written this way, curly bracket U is V. That's defined to be the sum over the degrees of freedom, that's an annoying thing to calculate, of di U by di Qi times di V by di Pi minus di U by di Pi times di V by di Qi. Alright, so I have to do those four partial derivatives and then sum them over all of the degrees of freedom. So it's an annoying thing that's happening. But it has some really interesting properties. So we found that there are some interesting properties of Poisson brackets. The first interesting property is that we can use a Poisson bracket to tell us how a quantity And that quantity could be a function of the canonical variables. So it's a function f of qi, pi, and t. How a quantity f evolves with time. And that's found, so the total time derivative of some quantity is given by taking the Poisson bracket of that quantity with the Hamiltonian. And then if that quantity depended explicitly on time, then you have to add di f by dt. So in particular, if the Poisson bracket of the quantity with the Hamiltonian is equal to 0, and di f by dt is equal to 0, then f is conserved. Conserved, of course, remember, means the time derivative of the thing is equal to 0. So this is often the easiest way to check if a quantity is conserved. You have a quantity expressed in terms of your generalized or your canonical variables. You can take the Poisson bracket of that quantity with the Hamiltonian, and if you get 0, then that quantity is conserved. So, okay, it requires that di f by dt is equal to 0. But if f depends explicitly on t, so di f by dt is not equal to 0, then it's unlikely that that quantity is going to be conserved anyway because it depends on time. Right, so it's a little bit annoying to have to say that because it's a little bit self-evident that, of course, if it depends on time, it's not conserved. But of course, for our mathematical friends, since we've written this equation like this, clearly we have to say that di f by dt is also equal to 0. Well, because of this thing about Poisson brackets telling us, especially Poisson brackets with the Hamiltonian, telling us how things change in time, we can use Poisson brackets to rewrite Hamilton's canonical equations in a nice form. So in particular, we could rewrite the canonical equations as qi dot is the Poisson bracket of qi with h, and pi dot was the Poisson bracket of pi with h. And then a final really neat thing about Poisson brackets is that we can use Poisson brackets between the coordinate and a conserved quantity to determine the transformation or the continuous transformation that leads from Mercer's theorem to that quantity being conserved. A mouthful. What I really mean is that Fi is equal to Qi with capital Q, Poisson bracket. So remember, in Mercer's theorem, you specified a transformation of the coordinates by specifying the Fi's and the G's. So it was up to you to come up with the right transformation and see if the Lagrangian was invariant. And if you did, then you'd find a quantity Q that's conserved. So you can go the other way around. If you know what the conserved quantity is, you can use Poisson brackets to figure out the coefficients of the transformation that lead to the symmetry related to that quantity being conserved. So it's actually really, really neat. It's a bit of a mouthful to say, but it's a very interesting property of Poisson brackets. Now, then we introduce canonical transformations. So canonical transformations from the coordinates, the canonical coordinates, canonical variables, lowercase qi and lowercase pi, to new coordinates, capital Qi and capital Pi. And the transformation is canonical if, so the Hamiltonian of lowercase qi, lowercase pi, and t transform to some new Hamiltonian k, which depends on capital Qi, capital Pi, and t. This transformation, or a transformation from lowercase q's and p's to uppercase q's and p's, is canonical if, when you've calculated the new Hamiltonian, the canonical equations are still true. So that means that capital Qi dot is still given by taking the partial derivative of the new Hamiltonian with respect to capital Pi, and then capital Pi dot was given by minus the partial derivative of k with respect to capital Qi. So that's what a canonical transformation is. It means you found a new set of coordinates, capital Q and capital P, in which the Hamiltonian still gives Hamilton's canonical equations for the equations of motion. So then we saw that we can construct a canonical transformation using a generating function f. A generating function f. So this generating function f, as we saw, needs to mix the dependence on the old coordinates and the new coordinates. So we never really specified how you can find this function f, but given that you have a function f that depends on the new and old coordinates, we can use it to make a transformation that's guaranteed to be canonical. So for example, for what's called type 1 canonical transformation, PT, f is a function of the lowercase qi and the capital Qi and t. So you can see there's 4 possible types, whether you mix lowercase q with capital Q or capital P, and lowercase p with capital Q or capital P. That's 4 possible ways to combine them by mixing them. Okay. So for type 1 canonical transformation, the transformation equations, so how do you go from lowercase q's to uppercase q's? Transformation equations are given by, so the lowercase pi's are found by taking di f by di lowercase qi, and the capital pi's are given by taking minus di by di capital qi of f. So you can combine these two equations for a specific problem, so you can get what Q is as a function of lowercase q and lowercase p and p. And you can find what the capital P's are in terms of the QI's and PI's. So yeah, you take these transformations that are given by the generating function, that will give you the equations that relate the P's and Q's together, and then you can massage those to get real transformation equations between the capital Q's and the lowercase q's and p's. And then the transformed Hamiltonian K is given by the original Hamiltonian. Well, let me write K as a function of the Q's and P's just to be strict. So we have K depends on the QI, capital PI's and P's, and that's given by the original Hamiltonian and the lowercase variables, plus the partial time derivative of the generating function. So given this formalism of canonical transformations, we saw that we could really make these capital Q's and P's quite arbitrary. And in fact, they had very little to do with position and momentum. We saw an example of a canonical transformation that actually inverted positions with momentum. So the capital Q's were equal to the lowercase p's, and the capital P's were equal to the lowercase q's. So this formalism of the canonical transformations allows you to escape your limitation in thinking of Q's and P's as position and momentum coordinates. What they really are a set of two n numbers that describe the system. And you don't have to be limited to thinking them as position and momentum. So that's really what canonical transformation does. It makes sense. It allows you to use completely arbitrary variables to describe your system. And there's a bit of annoying math to show that Poisson brackets are conserved by canonical transformations. So we showed that Poisson brackets are invariant to canonical transformations. By that I mean that maybe it's easier for me to calculate the Poisson bracket in the lowercase q's and p's. But I want to know what its value is in the capital Q's and p's. So because a Poisson bracket, we call that canonical invariant, I can evaluate the Poisson bracket in any of the coordinate systems that are related by canonical transformations. In particular, we can use Poisson brackets to test if a transformation is canonical. And that turns out to be the easiest way to do it. Test if a transformation is canonical. And the transformation is canonical if the Poisson bracket of the capital QI's with capital PI's is equal to delta ij, where it's equal to 1 if I is equal to j and 0 otherwise. And if you take the Poisson bracket of the QI with a different QJ, that's got to be equal to the Poisson bracket of the PI with a different PJ, and that's got to be equal to 0. Remember, those relations are true generally, and they remain true after canonical transformation. And these are easy to evaluate. So the assignment is due this week. Basically, you need to calculate the Poisson brackets to see if the transformations are canonical. And they're almost all one-liners, except some of the derivatives are annoying. So Poisson brackets seem annoying, but they turn out often to be the easiest way to test things. They're the easiest way to test if something is conserved, because you take the Poisson bracket with the Hamiltonian and you're done. And also the easiest way to test if the transformation is canonical. Then we went on a little bit of a crazy tangent. And we saw that we can use Poisson brackets to obtain an infinitesimal canonical transformation from a generating function, an arbitrary generating function. Well, let me just say from a function instead of generating function. Because that function need not depend on a mix of new and old variables. It could depend just on the old variables. But I'll call it G for generating. So an infinitesimal canonical transformation is a transformation where the capital QI's are equal to the original QI's plus just a little bit delta QI, same with the PI. So the new Q's and P's are very close to the original Q's and P's. And so the delta QI could be written, from what we've seen before, as epsilon times the Poisson bracket of QI and G. And the delta PI could also be written as the epsilon times the Poisson bracket of PI with G. That's on a parentheses plus a curly bracket. In particular, if G is the Hamiltonian, that's me closing the window by mistake, not the connection. In particular, if this function that we're going to use to make this arbitrary transformation is the Hamiltonian, then the transformation takes the system through time. That's the best way to phrase it. So remember, you take the Poisson bracket of a coordinate, qi, with the Hamiltonian h, you get qi dot. So the transformation capital Qi, the transformed version, is equal to lowercase qi plus epsilon times qi dot. So if you think of epsilon as being maybe a small increment in time, or a small number, it doesn't matter, then capital Qi is the original Qi plus a small amount of time, a small number times the time derivative of Qi dot. So capital Qi is lowercase qi a little bit later. So the Hamiltonian generates the canonical transformation that moves the coordinates through time. That's remarkable. And again, remember the Hamiltonian is related to energy, right? Hamiltonian is often the total energy. Conservation of energy has to do with symmetry with respect to time. And so then you get this amazing fact. So it's canonical, right? Because if you have a system that's evolving through time, the canonical equations must still be satisfied. The equations of motion are true at all times. So it's a valid canonical transformation to say, I'm going to go from the coordinates now to the coordinates later. That is a subset of possible canonical transformation. And it turns out that the generating function for that transformation is the Hamiltonian. But that should blow your mind. So then, we searched for a canonical transformation that would make all the variables cyclic. That would make all variables cyclic. And we did this using type 2 canonical transformation. So that's where F2 is given as a function of the lowercase qi and the capital Pi's in P. We did this using a type 2 canonical transformation and requiring that the transformed Hamiltonian K is equal to 0. So the transformed Hamiltonian K depends on capital Qi, capital Pi, and T. That's equal to the original Hamiltonian, which depends on lowercase qi, lowercase pi, and t, plus di F2 by di t. That's just the transformation equation. So we required that to be equal to 0. So if you take this at face value, you have an equation that says the Hamiltonian plus di F2 by di t is equal to 0. That's a differential equation for F2. So we don't know what the canonical transformation is, and we don't know what the generating function for that canonical transformation is. But by imposing that k is equal to 0, we now have a differential equation in principle that we can solve for F2 that will give us the canonical transformation that makes all variables cyclic. Because if the transformed Hamiltonian k is 0, then all the variables are cyclic. Alright, so if k equals to 0, then from Hamilton's canonical equations, we have capital Qi dot is equal to di k by di capital Pi. Of course, k is 0, so di k by di capital Pi is 0. So Qi dot is 0, and Qi is then a constant. Same thing with Pi dot. Pi is minus di k by di Qi. That's equal to 0. And so then what we say is that Qi is a constant, and we label that constant beta I. And similarly, the Pi's are all constant, and we label them alpha I. We make the P's alpha because it's the P's that appear in the generating function F2. F2 depends on lowercase qi and capital Pi. Okay, so now the solution for the equations of motion in the transformed variables is trivial. All the capital Qi's are equal to constant beta i's, and all the capital Pi's are equal to constant alpha i's. Those constants are just determined by the initial position of the system in phase space, in the capital Q and capital P phase space. Those can all be measured at some point in time, and then those things stay constant. So, for a type 2 transformation, the transformation equations are that lowercase pi is given by di f2 by di lowercase qi, and capital Qi is given by di f2 by di capital Pi. Right, f2 depends on lowercase q and capital P. So then the transformation equations are how do I get lowercase p and capital Q from f2. If I write those transformation equations down again, so the lowercase pi I'm just going to say is di f2 by di lowercase qi, same thing. But the capital Qi's, they're equal to beta i's. I'm going to write them as di f2 by di alpha I. I'm just rewriting the second equation here, but I'm replacing the capital Q's by betas and the capital P's by alphas, since I know they're constant. And then by convention, instead of writing the generating function as f2 that depends on lowercase qi, capital Pi, and t, we write it as the function s of lowercase qi, but now instead of capital Pi, I'm going to use alpha i's and t. And that is called Hamilton's principal function. So again, another awkward change in notation to reuse another letter that we've been using before, because we've been using capital S as the action. Now we're going to use capital S as Hamilton's principal function. So remember, the differential equation that we had was that h of qi and pi and t plus di f2 by di t is equal to 0. And I said that that's a differential equation that allows us to find f2. So let me just rewrite this equation, but instead of f2, I'm going to call it s. And the other thing I'm going to do, instead of lowercase pi, instead of in the Hamiltonian, lowercase pi is given by di f2 by di qi. That's the same as di s by di qi, since f2 which is relabeling. Okay, so instead of having h of qi, lowercase pi, and t plus di f2 by di t equals to 0, I'm going to write this as the Hamiltonian. So instead of qi, I'm going to leave, instead of pi we write that as di-s by di lowercase qi and t plus di-s by di-t equals to 0. And that is a partial differential equation for S, which depends on qi, alpha I, and t. And that equation is called the Hamilton-Jacobi equation. And so that allows us to find the generating function that makes all the variables cyclic. Of course, the partial differential equation itself may not be easy to solve. In fact, partial differential equations are generally non-trivial. Whereas ordinary differential equations, you can always integrate them numerically. Partial differential equations, that's not even true. You usually have to be clever. Whereas an ordinary one, you can be dumb and still solve it. I mean, you could be a computer and not put much thought into it. Now, what was, I think, the most remarkable thing in the whole course, we found that Hamilton's principal function is equal to the action S, remember that's the integral of L dt, within an additive constant. Within an additive constant. That doesn't change the equations of motion. So I made the comment earlier that we're going to put Hamilton's principle, the principle of least action, or the principle that the action must be stationary, we're going to put that on a pedestal and make that the founding principle of all of classical mechanics. So that action must be special somehow. It turns out, through the Hamilton-Jacobi equation, that the action is the generating function of a canonical transformation that makes the resulting Hamiltonian 0. It's not some arbitrary thing. It's a very special thing. And now, of course, you can make this the founding principle of classical mechanics. Okay, so I hope you grasp some importance of this action. The last thing that we did was we finished the complete change of topics back to Lagrangian mechanics. So we finished by considering how to model continuous systems. And found that we should use fields instead of generalized coordinates. So in the discrete classical mechanics that we have done thus far, the goal was to describe how the generalized coordinates qy evolve with time. We found that for a continuous system, it's not the qi's that we want to describe how they change with time. It's a new thing called a field. So we did this as an example. We did longitudinal waves in a string. So we initially modeled the string as a bunch of point masses connected by springs. Right, and then we could have said each mass had a coordinate qi. And then the goal of describing the string is to figure out how all the qi's change with time, and presumably they vibrate somehow. So we went from there to a continuous string. And now the idea was to describe some mass element and how it moves with time. And so we went from qi of t to a field, which we labeled eta, the Greek letter, of x and t. So eta is the displacement of some small element of mass located at position x at time t. So instead of having discrete coordinates qi, we have a continuous thing called the field eta. And the difference between a field and a coordinate is that a field depends on space as well. The coordinates are basically where you are in space. The field is a thing that depends on space and time. And so that's sort of the formal definition. Of course, you've encountered fields before when you've talked about the electric field or the magnetic field, and they're things that can change in space and time. So then we found that we should use the Lagrangian density instead of the Lagrangian. We found that the Lagrangian, if I limit myself to the one spatial dimension, the Lagrangian is the integral over space of the Lagrangian density, which I write as script L. The Lagrangian density depends on the field, eta. It depends on the time derivative of the field, d eta by dt. It depends on the spatial derivative of the field, d eta by dx. And then it depends on t and x. And that's integrated over dx. So then we found the Euler-Lagrange equation for fields. So what we did to do that, we did the same thing we did in before for the discrete case. We took the action, and the action is the total time derivative of the Lagrangian. So it's thus the double derivative of the Lagrangian density, because you have to integrate over space and then integrate over time. So we required the action to be stationary. And then we found the equivalent Euler-Lagrange equation for the continuous case of fields. And that equation, in one spatial dimension, is d by dt of di Lagrangian density by di eta dot plus d by dx of di Lagrangian density by di eta prime. Eta prime is d eta by dx, and eta dot is d eta by dt, minus di Lagrangian density by di eta. equals to 0 in one spatial dimension. If there was a x, y, and z, then you'd have a corresponding term for x, y, and z. So you can see how the notation becomes cumbersome, because then I need a different thing than a prime to say the derivative with respect to y. It turns out you should completely change notation before proceeding into 3 dimensions, and so I didn't do that part. So this Euler-Lagrange equation for the Lagrangian density and involving the field is very, very similar to the Euler-Lagrange equation that we have for the generalized coordinates. This is an equation for the function eta of x and t. It's not just an equation, it's a partial differential equation, because we have derivatives with respect to x and t. We're mixing the variables. It's going to be much more annoying to solve. But it looks very, very similar to the Euler-Lagrange equation for the discrete case. For the discrete case, you don't have the middle term, but the other two terms are exactly the same, except that now instead of q's, we have etas. And so fundamentally, it's not that different. Mathematically, it's much more annoying to solve. So that's it. That's all that we did. Just that. So this is just a high-level summary. But this is the stuff that you need to understand for the exam. And of course, some of the derivations are too difficult once I have done. In general, I don't expect you to memorize anything. But I do expect you to understand things. So even if during the exam you forgot to write down some formula you didn't memorize, just ask me. We really don't care if you memorize things. But I do care if you've understood things. And that's what's important. So it's important to understand the bullets in the summary. It's not necessarily important to be able to prove them. Okay? Any questions?